Okay, so we're going to go over the conversion from NFA to DFA. So non-deterministic to deterministic. So usually in an NFA, you might see all these different choices. You'll see lambda. I'm going to go over this NFA real quick. So basically, you'll have your states. So here in this example, I have 5 states. And basically you can transition to the different states depending on the input. So the only different inputs I have for this language or for this machine is A and B. So basically if I have an A, if the input's A, I can go from the initial state. If I have an A, I can go from the initial state to Q1. And then if I have a B, I can go from Q1 state to Q2. And so if my input was, let's see here, if my input was A, then I can go to Q1. If my next input was B into the machine, I can go to Q2. If my third input was A, I can go to Q5. Q5 has an extra circle around it. That's basically symbolic, that is an accepting state or a final state. So in a machine, if I had ABA, that is accepted by this machine because I can transition to this state, then I can use B to go to Q2, I can use A to go to Q5, and since that's the end, it is in a final state or an accepting state. Okay, let's go over some other inputs that would be accepted by this machine just to get you to understand. I'm not going to put lambda here. So lambda is kind of basically empty string in a sense, or nothing. It's almost like a free ticket. So let's see here. Let's say I have the input. So input A, so I can either go from Q0 to Q1, or I can say, hey, there's a lambda in front of the A because it's basically empty. I can get a free ride, a free ticket to state 2, and then I can use A to transition from Q2 to Q5. Okay, so kind of enough with that. Let's do the conversion from NFA to DFA. So basically what we're going to start out with is we want to find all the lambda transitions. Okay. So basically all the free tickets. Let's get that out of the way. So let's find the lambda transitions of state 0. So for lambda transitions, or lambda closures, we are always going to have itself. So Q0. Basically why that is basically you can pretend that you have a self loop with lambda. You can always get back to yourself with a lambda. So lambda closure of Q0, we can get back to Q0, or it looks like we got a ticket here. We can use lambda to go to Q2. Okay. No other transitions, so using lambda, that's the only, we have itself, you can always go to itself. And by the way, this is the initial state that's going to be symbolized using this arrow. I forgot to add that. So lambda closure, you always have yourself, and then whatever lambda you can use to get to another state. So in this case, we can go from Q0 to Q2 using lambda, almost as a ticket. Okay, let's do lambda closure of Q1. So let's go to Q1. So like I said, you always have a ticket to yourself, or you can always use lambda to loop back and go to yourself. So Q1 is going to be in there. And we don't have any other paths to travel using lambda, so that is actually it. Let's do lambda closure of Q2. Let's go to Q2, which is a state. Remember, you can always go back to yourself using lambda. So Q2. So you can think of lambda closures almost like free rides. So no other paths or states I can travel to using lambda. So that's it for Q2 as well. Let's go to Q3. Let's do, and we'll kind of divide this, lambda closure of Q3. Let's go to Q3. Always loop back to yourself, so we can use Q3, and then lambda closure to Q0. Okay, and then since we can get to Q0, I'll double check my notes here. So Q3, we do this two ways. We could say, hey, since we're arriving at Q0, we know that we can also keep using the lambda closure from this set. But obviously you can look and say, hey, I was at Q3. You can use lambda as many times as you want. I can use lambda, get to Q0. Once you get to Q0, I can also get to Q2 using lambda again. So Q2 is also going to be a part of that lambda closure. It's basically saying, hey, from Q3, how far can I reach out without needing some kind of input? How far can I travel with just using lambdas, lambda closure? That's basically the definition. Is how far can I travel from Q2 just using lambda transitions. Okay, so let's do lambda closure of Q4. We can always loop back to ourselves using lambda, so Q4 is going to be included. Let's go to Q4. So looks like we can transition using lambda to go to Q3. We can transition to, and instead of following this, let's just say, hey, we can get to Q3, and we know Q3, we can travel to Q0 and Q2. So Q0 and Q2. So basically we can just use the lambda closure of Q3. So Q0 and Q2. All right, and then last but not least, the Q5, lambda closure of Q5. Always go back to yourself. And we can see from Q5, we can go to Q4. We can't really branch out to anything else except for Q4. So we know that we can pick up all the lambda closures or all the free rides that lambda closure of Q4 had. So we're missing Q3, Q0, and Q2. Q3, Q0, and Q2. Okay, so we have all of our closures. Wish I had more room here. Let me kind of erase this stuff. And actually, I might erase this. Yeah, I'm just gonna go ahead and erase this now that we got our states, our lambda closures. And I'll just reference my sheet here. Okay, so basically now I'm going to build a table, and this is going to help us convert to a DFA. So I'm going to have a column A and a column B, and these are basically my transitions here. We're going to start out with P0. basically the goal is to, obviously you don't want it to be non-deterministic anymore. You want it to be deterministic where the machine doesn't have all these choices. And your end goal, I mean, this won't find you the most minimal DFA, but it should reduce the number of states. But after you find this table and you create the DFA, you might have to do some more work to find the most minimal number of states for that DFA. Okay. So, in our transition column, we're going to have Q0 to Q2. We're going to start out with this guy here. I might have to redraw this. I'll probably redraw this over here. Cut that out in the video. Basically, yeah, let me just redraw this. I'll cut this out. Just make it smaller this time. Q0 lambda Q1 Q2 lambda transition. That uses B, that uses A. This uses A for transition. Q5. Q4. Lambda A Q3 lambda and again. Okay. So Q0, Q2. Okay, so basically go to Q0 and say, hey, with input A, where can we go? So from Q0 with input A, we can see that we can go to Q1. Okay. And then, so no other transitions can we make with input A. So let's go to Q2. Q2, what transitions can we make with input A? Where can we go from Q2? We can go to Q5. Q5. Now this is where our lambda closures are going to come in to play, because you notice from Q0 we can use lambda, then we can use our input A, because we can have a free ride and then we can grab our A. So basically what we're going to do is grab all of our transition or closure, our lambda closures for Q1, which is Q1. So basically, no, we can get to A, but can we use any lambda closures to keep going? No, we can't. We already figured that out in our lambda closure list. Q1, if we use input A to get to Q1, we can't use any lambdas to transition, and that's what that says here. So Q1 only has Q1. Let's check Q5. Once we get to Q5, so from Q2 to A, we used our input A. Can we use any lambdas to keep going? Let's go to Q5, lambda closures. Yes, we can. We have Q4, Q3, Q0 and Q2. Q0, let's